Hey YouTubers, today I wanted to talk about some underground medium voltage cable. So what you see here is about a 3/16 inch thick wafer of a 35 kV cable. When I say 35 kV, the insulation is rated for 35 kV, but that's three phase. So single phase, what you actually have running through this is about 19,900 volts to ground. It's basically the 1.73 times the individual phase conductor is how you get your three phase. So you have 19.9 running through this, but the voltage rating on it is 35 kV. We'll just start with the layers really quickly. The first is your conductor, which actually has your current running through it. You've got your conductor shield, this black layer. The white is your insulation. Then the black is your semicon. Then your concentric neutral layer with the copper there. And then lastly is the jacket. So we'll talk about the conductor first. So this is an aluminum conductor. Obviously there's copper. It's mainly copper and aluminum. That's your two different types of wire for this industry. Silver is actually the most conductive metal, but of course, silver cable would be ridiculously expensive and would never offset the losses. Then next you have copper, then gold, and aluminum. There's a number of different types of conductor. There's solid conductor, which is just one solid piece of metal. You've got stranded, which is the configuration this is. And then you have compressed, where in the process they compress these together. And then the compact conductor. The compact is the second most efficient, solid being the first. But when you're installing things in conduit, there's no way you can have this be a solid piece of aluminum. There's no way you could install it. There's no way you could pull it through pipe. So really the compact and the compressed are the next best efficient way to go in the stranded configuration like this is. This to me looks like it's compressed. It's definitely not compact because these are pretty round. I'm thinking that it's compressed because the outer ones aren't perfectly round. They do have a bit of squish to them. So really the name of the game is to keep this as malleable as possible for easy installation, but have as few air gaps here as possible, because that's just inefficiency and losses. And that also causes flux on this outside ring that we'll talk about next. So that's the conductor. Again, copper and aluminum. The main ones that you see in cable like this for wind farms, it's usually always aluminum just because of the cost offset. The next layer is the conductor shield. And it's actually an XLPE type of polyethylene, but it's mixed with carbon black. I think the technical name for it is acetylene black. And it actually comes from a byproduct of acetylene. So you've probably seen somebody with an acetylene torch. When they first light it, you see a lot of that black smoke and black soot. The process of getting this acetylene black is capturing that and refining it. It's extremely conductive. So they mix that acetylene black with the XLPE insulation, and that's why it's black, obviously. The purpose of that is to try to even out the lines of flux. So there's inefficiencies here in the edge of the cable, and you have a lot of flux coming off of this, wanting to head to ground. And you may have more in one area than you will the other, because this isn't a perfectly round, symmetrical cable. So the purpose of that is to take some of that flux out and begin to sort of even it out. Why do we want it evened out? That's what we'll talk about next. So the insulation here, this white, is XLPE. They have a lot of different types of insulation. There's another popular one is EPR. That's kind of orangish looking, sometimes almost red looking. And this XLPE. There's also paper insulation. You can use oil, but these are the most common, EPR and XLPE. So the XLPE is more efficient. It has about a 25% more higher breakdown strength and 70% higher impulse strength. So that's an impulse strength is high voltage, high current for a short pulse. This XLPE is good from -40 to 105 Celsius with an emergency rating of 140 C. I don't remember what the duration is for emergency rating. I want to say 2 hours. but it's only a temporary for that 140C. The EPR, on the other hand, it's more of a rubber, and it's way easier to install. It's more flexible. It's a little bit more difficult to strip the semicon, which is the next layer. And the EPR is good from -60 to +150. So it does actually have a wider heat range than the XLPE. Plus the EPR is about 10% higher in cost. So overall, the XLPE is a great insulation, and it's mainly used on the wind farms. And this is 345 mils, which is 345 thousandths thickness. There's a lot of IEEE tables and just different tables that will tell you what the insulation thickness is supposed to be. You can actually buy cable with a higher insulation rating than you need to. This is a 100% insulation, which means that that's what you need to operate this cable safely. You can also purchase 133% and 166%. A lot of people like that extra fluff in there. If you've got, transient voltages and things like that, that you want to make sure don't break your insulation down over time, that's when you'd see things like that. This here is 100% insulation, and it's called XLPE, and it's actually fairly transparent. I don't know if you can see that too well. It depends on the thickness that you cut this. An interesting fact, when you send this in for testing, they put this in a hot oil bath, and this white insulation actually turns clear, and you can see any type of inefficiencies in this cable. If you're doing PD testing can identify bad sections of cable, and usually when you do that, you get a microscope and you can actually see a miniature bubble or two in there. So really kind of a crazy process for it. And how they make this is they actually extrude it at a few layers at the same time under a lot of heat and a lot of pressure. The conductor goes into the extrusion machine, and it puts the insulation shield on, it puts the insulation on, and it puts the semiconductive layer on as well, which is called the insulation shield. So this one is the insulation shield, the other one is the conductor shield. So we'll talk about the insulation shield next. That's actually the same material as the conductor shield. It is a semiconductive layer. It's a polyethylene mixed with the acetylene black. That's what gives it the black color, and that's what allows it to be semiconductive, is because of that acetylene black conductive material impregnated into it. So why do we need the semicon layer and that insulation shield? And it's to prolong the life. So how is that? So if you have a cable laying on the ground, right here, this is the ground, you're going to have bleed from the flux to ground. And if you do not have any of these layers, it's going to bleed right here. This is your conductor, this is your insulation, XLPE. It's all going to bleed through this part of the insulation, and it's going to break that insulation down over time. And that's what reduces the life of your cable. Going to this with the conductor shield and the insulation shield, same concept, but whether it's laying on the ground or not, with the insulation shield and that semicon layer, I'm a crappy drawer, everything's going to bleed evenly through that insulation to the semicon and to the concentric neutral layers. And what this does is allows even breakdown of the insulation over time. And when I say over time, we're talking 20 years at a minimum. That's typically the life of this cable. It actually lasts up to 40, 50 years even. And there's some cable that's out there that lasts even longer. The main reason for that is the even distribution of flux through the insulation to that semicon and to the ground. So that's the main reason why. And we just talked about the insulation shield. The next layer is called the concentric neutral layer. This could be, in this case, they're copper conductors, bare of course. You can see tape shields, which is a piece of copper tape that wraps around. There's also flat strap cable as well. It's basically these, but flat instead of round. It's a little bit cheaper to manufacture that way. So what these are, I want to say that this is a 21 number 14 CN, concentric neutral. What 2114 means, it's easy. 21 of number 14 gauge copper conductors. That's it. What determines the size of this? The fault current decides the size of that. So if you have, say, just one example, a much larger main power transformer that has a higher fault current, you're going to see a lot more of these concentric neutrals, and the size is probably going to be bigger. It might be a number 12 or number 10. There could be 30 of them. So what determines that is the fault current. And probably the most, the item that affects the cost of this cable the most isn't, well, number one is the size, because you're going to have the most material. And the second one is your concentric neutral layer. Why is that? Well, it's because it's copper. Copper is a lot more expensive than the aluminum. So the name of the game, really, with the engineers is to have them run their fault current study and determine the minimum size concentric neutral required for that project to maintain a safe project. So you want to put a lot of time and money into that, because you'll get that money back in being able to potentially reduce your concentric neutral. So very important for that. This layer basically kind of keeps this insulation shield grounded. Again, it's evenly distributed around that semicon layer. So as the lines of flux bleed through the insulation evenly, they're ultimately bleeding to these concentric neutrals, which at the terminations on either side are grounded. So this is the actual grounded layer. So it's pretty crazy to think about it. Between this energized conductor that has 20,000 volts on it, 19,900 to ground, which is 35 kV 3-phase, you only have, this is, half an inch, a little bit more than half an inch to ground. So imagine, a 10,000 PSI gas line. This electricity is looking for a way to jump out. And if you put even the smallest little pinhole, even something a quarter the size of a pinhole, it will jump out and it'll blow up the cable. I would say the most important layer of this cable is the insulation shield. If that gets punctured or cut or broken in any way, that flux will jump through, and the voltage will jump through the insulation to ground, and it'll blow up the cable. It's the most important part, this black area right here. So to help protect that insulation shield is this last layer, and that's the jacket. It serves no electrical function. It is simply there to protect the semicon and the cable from damage. That's all it does. It's extremely hard. You can actually try to take a knife to it and stab it. I doubt you're going to get through that layer. And this layer is either a PVC or an LLDPE layer. LLDPE is a little bit newer than the PVC, and it's better, in my opinion, because it's resistant to animals that like to bite and chew into things for whatever reason. They don't mind biting into the PVC, but they do mind eating into this LLDPE. They won't. It's also resistant to a wider amount of chemicals. Not that you're going to be spilling crazy chemicals on your cable, but it's just better having a slightly better and more resistant layer. So again, that's the LLDPE in this. We've installed cable without a jacket at all. And that's perfectly fine functionally. What you'll see on the outside are the concentric neutral layers. Nothing wrong with that at all. It's just not wise, in my opinion, because if you have a rock or anything like that may scrape or puncture through this semicon layer, you're done. It's going to blow up and you have to replace it. You probably see that layer. It's just a slightly different black. Focus. Slightly different black than the LLDPE layer. But that's what that is. So testing for this is, you can do high pot testing, which is an older technology. You can do VLF testing, very low frequency testing. I'll put a link up to a video I did on that here right now up in the corner. And then PD testing is the other test as well that we do on this. Another thing that we like to do is we'll trifoil the cable. It's almost all our wind farms we do this way, and what that does is cancels out the electromagnetic field, the EMF, with these cables, and it keeps the heating down. So believe it or not, you'll have less heating like this than you will if these are separated a lot further out. It cancels out that EMF field. So anyway, that in a nutshell is the 35 kV cable. I could talk 2 days straight on this stuff. That's really just high level. Again, your current carrying conductor, your conductor shield, your insulation shield, your concentric neutral layer, and your jacket. Thanks, guys.